All right, so what we're going to do is we're starting the last section, the last thing we're reviewing for review second unit B, I guess. This is going to be target 6, which is applications of integration. Now, we've already talked about some, well, a whole bunch actually, applications of integration. For instance, volume, area, all of those are applications of integration. I've already talked about where we do your new position equals your old position plus the integral of change. So whatever your movement you've done, so this is plus the change in your movement. Oh, that didn't spell change. Your change in your movement. So we've already done some applications of integration. Let me just show you the chart that I'm going to be giving you, or hopefully you may have already seen it because it's in your lessons. There's this big theorems of integration, this big table that organizes everything that we learned last year and some this year. So Riemann sums, we reviewed that a little bit this year. The fundamental theorem of calculus, of course, which is the area of the curve. Mean value theorem, which I'm going to talk about here in just a second. And then the average value, okay, which is the mean value theorem. Average value is just the mean value theorem written a little differently. And then the second fundamental theorem of calculus, I'm going to talk about that in a little bit. And then here's estimating quantities. This is where we have your amount now equals your initial amount or your old amount plus the change. That's this. That's using the fundamental theorem of calculus and just rewriting it. And then the sum of integrals is where you add up and you start getting areas and stuff. But this tells you that the sum of two integrals, you can add two together to get the whole thing. So like if you want the area all the way from A to B, you can add A to C plus C to B and get the total from A to B. So you can add integrals together. Then we've got these two things that I'm going to review here in just a second, just if you remember the concepts for inverse functions and growth and decay. And then all of this was the new stuff you learned. Area between two curves, and then here's all your disk, washer, cross sections, and shell. All right, so that's all applications of integration. All right, and we've done a lot of that already because some of it had to be new material. But I'm going to hit some of the highlights on this, but you've got this sheet that maybe you can print it off if you've got a printer or something. If not, at least get a picture of it or something to be able to look at it and study it, because those are all of our big theorems. All right. So what I want to talk about is hit some of the highlights of those that we haven't done yet already very much. All right, the first thing is fundamental theorem. All right, we've hit the fundamental theorem of calculus quite a bit when you're evaluating a definite integral. But the fundamental theorem of calculus, that leads you to that theorem where your new value equals your old value plus the change in your movement, all right, or plus the change that's happened. So I just wanted to give us another quick example since a couple of us have asked questions about that. So for instance, as an example, if we have V of t equals negative 2t plus 12, and I know that S of 0 is 28, and I want to find S of 4. That's what I want to find, all right? So I've given you the velocity and I'm giving you your starting position. Your starting position is 28. So where are we after 4 minutes or seconds, whatever the units are? So where are we at time 4? All right, so the way to do this is you do your new value, which is S of 4. That's going to equal my old value, S of 0, where I was at 0 time, plus the integral of change that's happened in this interval. So from 0 to 4, if I integrate my velocity, I will have the change in my position over that interval of time. All right, so S of 4 is going to equal my starting amount, 28, plus the integral from 0 to 4 over that time interval of my velocity, which is negative 2t plus 12. And so this is just applying the fundamental theorem of calculus and getting the answer. All right, so I have 28 plus, the antiderivative of this is going to be negative 2t squared over 2 plus 12t. You don't need your plus c because you're evaluating from 0 to 4. And so I'm going to do the fundamental theorem of calculus on this part and then add the 28 to it when I'm done. All right. So we do the fundamental theorem of calculus. So I'm going to put the 4 in first, and of course these 2's cancel. So that's going to be, putting a 4 in here will be negative 16, and putting a 4 in here will be plus 48. Then putting a 0 in for both of those is going to be 0. So my S of 4 is going to be 28 minus 16 plus 48. All right, so what is S of 4 going to be? Let's see, 28 minus 16 is going to be 12. And then when I add 12 to that, I get 60. So that means after the 4 minutes, seconds, or whatever the time frame was, I moved from 28 to 60. So I'm ended up at 60. All right, so that's my position at time 4. So that's using this idea that I knew an initial amount and I knew my velocity, which is my rate at which I'm changing. So where am I at a new value for? All right, so that's applying the fundamental theorem, writing it in a new way. All right, and that's all you're doing. So if you remember the fundamental theorem says when you evaluate a theorem or an integral, this is f prime, right, inside here. You do the antiderivative, so that'd be f of x, and then you evaluate it from a to b. So that gives you f of b minus f of a. And so really all you're doing is adding this f of a over to this side. So if you add f of a over here, so f of a plus the integral equals f of b. So what is that saying? This is my new position equals my old position plus the change that's happened. All right, so that's really just rewriting the fundamental theorem in a different way. That's all it is. All right, that's all that is. And then the next thing I wanted to talk to you about was mean value theorem for integrals. We've done the mean value theorem for from derivatives. So what is the mean value theorem for integrals? Well, the mean value theorem for integrals said that if you have a function and you're trying to find the area under it from a to b, there is some c value in here somewhere, we'll just say it's right there, that if you do a rectangle using this c value as your height, then the area underneath this curve for f of x, this is f of x, the area underneath that curve will equal whatever this width is right here, which is f of c. That's putting the c value into the function to get this height right here, times b minus a, which b minus a is this length. So this rectangle will estimate the area underneath the curve. So the area under the curve will equal the length and the width multiplied together for the rectangle, right? So we're saying there's a rectangle with equal area for some c value in the interval. So when you put c into the function, that gives you the width of that rectangle. That'll give you the same areas under the curve. All right, that's the mean value theorem. Okay, now in order for that to be true, the function has to be differentiable and continuous, right? Those two conditions have to hold. We have to be continuous and differentiable in order for that to be true. All right, then this is true. Now, when you rewrite the mean value theorem and solve for f of c, then you're dividing the b minus a, and this is your average value formula, if you remember that from last year. So this is average value. So whenever you see a problem that says find the average value of blah, 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 they're asking you to do that formula 1 over b minus a times the integral, okay? So if I gave you this problem, find the average value of y equals 2x squared plus 2x plus 1 on the interval from -2 to -1. So in order to find this, it has to be a continuous function, so mean value theorem has to apply. And this is a polynomial, so of course it's going to be continuous and differentiable. So there is an average value for this. So the formula for average value is just rewriting the mean value theorem. So it's 1 over b minus a times the integral from a to b of your function that you're taking the average of, right? And it's wanting us to take the average of this, so there's going to be our function. So our answer is 1 over b minus a, so -1 minus -2, which is going to make that a plus. And then the integral from -2 to -1 of the function 2x squared plus 2x plus 1. Now this is going to end up being a positive 1 in the bottom, so that's just going to be 1 over 1. So no big deal there. So my coefficient's gone. It's just 1. That's an easy one. So now I'm doing the antiderivative of this. Okay? So this will be 2x cubed over 3, because that's the antiderivative of that, plus 2x squared over 2, which is just x squared, plus x. And I don't need the plus c because I'm evaluating from, what was this, -2. I'm evaluating from -2 to -1. All right? So my coefficient, the 1 over b minus a, that ended up being 1 over positive 1, so that ended up canceling. Doesn't happen too often that that does happen, but that's nice that it did. All right, so now I'm going to do the fundamental theorem of calculus here. So I'll put a -1 in there. So when I put a -1 in there, that's still going to be -1, so it's -2/3. Putting a -1 in here, going to give me +1. Putting a -1 there gives me a -1. Then I'm going to put a -2 in here. -2 cubed is -8, so that's going to be -16 cubed. Putting a -2 in here will be +4. Putting a -2 in there will give me a -2. All right, so here these ones cancel, so I'm left with -2/3. If I distribute this across, I'll have a positive 16/3, and then I'll have a -4, and then a +2. So this is going to give me 14/3 and then -2. So 14/3 minus 6/3, because 2 is 6/3, and that's going to be 8/3. So there's my answer. So my answer is 8/3. That's the average value. Now, if the problem says to find the C value, that gives you the average value. This is the average value. So that means there's some f of c that gives me 8/3. So if the problem says find c, then you have to go back to this original equation up here and set it equal to 8/3, which I'm not sure that that's going to be a very nice answer. So there's some f of c, so that when you plug c into your function, you get the answer 8/3. All right, so that's what you would do if the problem asked you to find the c value. You would take whatever the answer you just got when you did the average value, set the function equal to the average value, and then solve. All right, so I just made this one up, so it's not going to be a nice answer, so we won't try to do one that doesn't turn out to be a nice answer. But that's all you do. You set your function equal to your average value to solve for the c value if the problem ever asked you to find the c value. So that's average value using that 1 over b minus a times the integral from a to b. All right, now the second thing I want to talk about is the second fundamental theorem of calculus, the next thing. All right, the second fundamental theorem of calculus was the one where you take the derivative of an integral. All right, so there has to be a number down here on the bottom. There has to be some number, and then there's some function up here. So there might be some function of x up here. And then there's a function behind this in a different letter. So it won't be in x's and match this up here. So this might be 2t plus 1 dt. So what you're asked to do, this is using the second fundamental theorem of calculus. That's, you're taking the derivative of an integral. That's the second fundamental theorem of calculus. You're taking the derivative of an integral. Now, in order for this rule to work, like I said, there has to be a number as your lower limit, and then your upper limit can be any function or anything up there. Okay? So to take the derivative of an integral, remember these cancel away. And what you do is you plug this thing into the function. So this ends up being 2 times f of x plus 1. So you plug the f of x, or whatever this function is up here, into the function for the variable, whatever the variable is. It's usually a t, but whatever it is, plug that into that function. Then you have to chain on the derivative of what you plugged in. So then I have to chain on f prime of x. So you just chain on the derivative of what you plugged in. All right, that's using the second fundamental theorem of calculus. So if I was doing a problem like this, from -2 to x squared of t cubed plus t minus 8. So let's say I was asked to do that problem. Taking the derivative of an integral, and it has a number at the bottom, all I do is plug this in. So I'm going to plug x squared in here. So I'm going to do x squared to the third power plus x squared minus 8. So that's the first thing I do is I plug x squared in. Then I multiply, because I'm plugging in something that's not just an x. Then I have to multiply by using the chain rule and multiply by the derivative of the x squared that I plugged in. All right, so my final answer here, when you raise a power to a power, you multiply. So this would be x to the 6th plus x squared minus 8 if I wanted to multiply this out. And then I would distribute the 2x in. So this would be 2x to the 7th plus 2x cubed minus 16x. So this would be my answer. So when you take the derivative of an integral, they cancel. But in order for the rule to work, you have to have a number at the bottom. And then whatever this function is, you plug it in. And then you chain on its derivative. That's how you take the derivative of an integral, which is the second fundamental theorem of calculus. Now, I kept saying you have to have a number at the bottom, right? So what if there's not a number at the bottom? So let's say I was doing the integral from x to x squared. Let's make that up. And we'll do t plus 1 just to make it simple for us, dt. So this one doesn't have a number at the bottom. So I cannot do this problem using the second fundamental theorem of calculus because it doesn't work with it. So what you have to do is you have to rewrite this problem. So I'm going to rewrite this integral as the integral from 0 to x squared minus the integral from 0 to x. And you can pick any number you want. It doesn't have to be 0. I just do 0 because 0 is easy. All right. So what I'm doing is I'm writing this as the integral from 0 all the way to x squared. And then I'm subtracting away 0 to x. So when you do that, all you have now is between x and x squared. So like if you had a graph, you're doing the area from 0 to x squared. And then you're going to subtract away the area from 0 to x. So that leaves you with just the area from x to x squared. So that's what I'm doing. So I'm rewriting this problem in a format that is going to work now. So now I'm taking the derivative of this difference now, because I just rewrote the integral as the difference of two other integrals that have a number as the lower limit. So now when I take the derivative of that, I'm going to apply the second fundamental theorem of calculus to each piece. So to take the derivative of this first piece, I plug in the x squared. So that'll be x squared plus 1. And then I have to multiply by the derivative of x squared. So that part's done. Minus, now I'm going to do the same thing over here. To take the derivative of this integral, I'm going to plug in the x. So that'll be quantity x plus 1, because it's a quantity. I need parentheses around it since it's subtraction. All right, so I plug the x in, and then you chain on the derivative of that, which is just a 1. So this is my answer. And if I wanted to multiply all that out, I could. Here, let me get rid of all that. If I want to multiply that out, I can. So that would give me 2x cubed plus 2x, and then this would be minus an x minus 1. So my final answer would be 2x cubed plus x, whoops, that was a 1, sorry, minus 1. So this is my answer. So 2x cubed plus x minus 1 would be the answer for the derivative of this integral, because I wrote it as two separate integrals so that the rule could apply for the second fundamental theorem. And then I applied the second fundamental theorem to both pieces, and voila, I got the answer. Now you can also do all the work. You can do the antiderivative and then do the fundamental theorem, and that'll give you the same answer. So what I'm saying is you could do t to the second power divided by 2 plus t, and then do the fundamental theorem and evaluate it from x to x squared, and it'll give you the same answer. But it's nice if you can do the second fundamental theorem of calculus and make it a little easier on yourself. All right, now the last thing I just want to hit the highlights of, because I've done the main big theorems that I wanted to talk about. So I wanted to hit the derivative of inverse functions, just to remind you of that rule. All right, so if you remember inverse functions, that's when you switch your domain. And so to find the derivative of an inverse function, so if I have some function y equals f of x, and I know his derivative, let's say, and I'm trying to find, and I know his derivative at x, just making up numbers, at x equals 2. So I have some function, f of x, and I want to find the value of the derivative at 2. Then I would take the derivative, plug in 2. Let's just say I get the answer of, I don't know, 14. All right. So that means my slope of my tangent line for this function at 2 is 14. So now what if I wanted to do another function, which is the inverse of this guy over here? So let's say I wanted to do the inverse function and do his derivative at, let's see, if this is 2, let's just say this point is going to be the y value here for 2 for this function. Let's say the y value is going to be 5. So now over here, I want to find the value at x equals 5. So remember, because their domain and range switch. So for this function, x is 2 and y is 5. But for the inverse, my x would be 5 and the y would be 2. All right, I'm just trying not to come up with specific functions. All right, so remember your domain and range switch. So over here, if I've got the inverse function of f, and I'm trying to find its value of the derivative at 5, which is the y coordinate of this one, the relationship here that we learned is that these derivatives, these answers, are going to be reciprocals of each other. That's what we learned last year, that the derivative of the inverse function at the mirror point, remember we talked about the reverse mirror point, the derivatives of those guys, the function and its inverse, the derivatives are reciprocals of each other. That's what we learned last year about inverse functions, that you don't need to be able to figure out the derivative of the inverse. If you already know the derivative of the function, then all you got to do to find the derivative of the inverse at the mirror point is just to flip it upside down. All right, that's what we learned last year. So that's all I wanted to refresh your memory about. It's just knowing that relationship, that those are inverses of each other. Okay, and then the last thing I wanted to refresh your memory about was growth and decay, because that's mentioned in that table. For growth and decay, those are problems where we have y equals, y prime equals ky. That's where the change in the value is proportional to itself. And every time we did the dy dx equals ky, and then we brought the y over here and the dx over here and we integrated. And every time we did the calculus, it always led to this equation from last year. Y'all remember this? And you can either use an R or a K. It just depends on. So I call it the CERT formula. So C equals C times E to the RT. So Y equals CE to the RT, or KT, depending on if you want to use a K. So here, if this is a K, this would be a K right here. So it just depends on whether you see the version with the K or the T. I call it the CERT formula, so I put the R in there all the time. But I just want you to remember that if you start out with this situation, Y prime equals some constant of proportionality times Y, that always leads to this formula. Y equals CE to the KT, where this K is this K right here. All right, so that always leads to that. I just wanted to remind you of that, because sometimes on the AP exam, they just ask you which one of the following equations satisfies this differential equation. So if you just know that this differential equation should have an answer like this, then you pick the one that looks like that. That's all that is. So those are the main things I wanted to hit upon for big theorems of integration. So you've got some problems to practice. And then, of course, we have a sync time to get together to be able to do some problems and ask some questions. So work on your practice problems. Go through this little table of information that I gave you to make sure you remember each of those different concepts. Make sure you remember about the fundamental theorem and then the second fundamental theorem, and do that circuit and apply those properties there. And I'll answer any questions you have during our sync time.